All right, so now we're going to take a look at some of the factors that affect solubility. And the first one we're going to take a look at actually is something we saw previously, and that is temperature. Okay, and then generally, we're going to say that for solid solutes, you'll notice that all of your KSP values have a temperature associated with them. So for solid solutes, what we find is that as temperature increases, okay, we can dissolve more of the solid in there, so solubility increases as well. And then for gas solutes, the opposite is true. So as temperature goes up, less of a gas is able to dissolve, so solubility decreases. Okay, and this has this goes back to what we saw in Gen Chem 1. These are actually things we talked about in General Chemistry 1. But these are factors that do affect solubility, so I still need to remind you of these here. So recall from Gen Chem 1. Okay, and now we're going to get into now some of the equilibrium aspects of this. So the first one we're going to spend a little bit more time on is called the common ion effect, which we introduced at the beginning of this section. We're also going to take a look at how pH can affect solubility, as well as the formation of complex ions. So we've seen that the solubility product is an equilibrium constant, and precipitation of an ionic compound from a solution occurs when the ion product exceeds the KSP for that particular substance, right? So remember, for something like AgCl, for instance, right, we can look up the solubility, and we can see that if we multiply the AAG plus times the Cl minus, right, we end up with 1.6 times 10 to the minus 10. So this means our S squared is 1.6 times 10 to the minus 10. Okay, which means then that S is 1.3 times 10 to the minus 5 molar. And that is the solubility of AgCl. Okay, these are the things we talked about in the previous section. So S still represents the concentration of the Cl minus, for example, and the Ag plus, and it's also the solubility of AgCl. So let's take a look at an example of, again, using silver chloride, but now it says calculate the molar solubility of silver chloride in a solution that is 6.5 times 10 to the minus 3 in silver nitrate, right? So now we wanted to determine the solubility of AgCl in a solution that already contains a solute that has a common ion. So silver nitrate, right, has a common ion, and that common ion is the silver ion. Right, so an Ag, the AgCl system, right, we know that that produces the Ag plus and the Cl minus. The Ag plus from the silver nitrate, this solution here, is common to our equilibrium system. All right, so because it's a strong electrolyte, all nitrates are soluble. This will dissociate completely to give me the Ag plus and the NO3 minus. If the concentration of the AgNO3 is 6.5 times 10 to the minus 3 molar, this is also going to be the concentration of the Ag plus. 6.5 times 10 to the minus 3 molar. So even before so the concentration of the Ag plus, even before any of the Ag from the silver chloride dissolves, is already, so if I write my ice table, right, initially I already have some of the AgCl, right, the 6.5 times 10 to the negative 3. I have none of the chloride to begin with. Then as this reaction proceeds, as the AgCl now proceeds, I'm going to gain S. I'm going to gain S over here. And then at equilibrium now I have 6.5 times 10 to the minus 3 plus S. And then here I have S as well. Okay, and that's based on our equilibrium system, based on this one, where the KSB is equal to the Ag plus times the Cl minus, right? We're starting off with this amount of the Ag plus because that's coming from the silver nitrate that's providing that common ion. So if we substitute that into now our equilibrium expression, our KSB expression to be more specific, we can look up the KSB for silver chloride, and that's 1.6 times 10 to the negative 10, and that's equal to 6.5 times 10 to the minus 3 plus S, whoops. Times S here. Again, we're going to assume that S is small. Okay, this is the same technique we used in the previous equilibrium systems. We're going to expect S to be small because this is a sparingly soluble salt. Silver chloride is. So then we end up with 1.6 times 10 to the minus 10 is equal to 6.5 times 10 to the minus 3 times S. So then S would be, we solve for X. Okay, do a little bit of math on this. And this ends up being 2.5 times 10 to the minus 8. And that's what we get for S. Or what is S? S is the concentration of the chloride ion in solution. And it's also the molar solubility of the AgCl in that silver nitrate solution, right? So this here is now the molar solubility of AgCl in that 6.5 times 10 to the minus 3 molar silver nitrate solution. So what does that actually tell us? Well, it tells us, if we compare the solubility of the silver chloride just on its own, which was 1.3 times 10 to the minus 5. So that's just the molar solubility of AgCl. And we compare that to what we just calculated, 2.5 times 10 to the minus 8. Okay, so let me write that here so we can compare it to 1.3 times 10 to the minus 5. In just in water on its own, right, we can see that having that common ion suppresses or reduces the solubility of the AgCl in this case. And that would it should make sense, because if we are affecting this equilibrium by introducing more of the stuff on the product side, it will force the equilibrium to the left, right, which will reduce the solubility. Now on the left side, we have our undissociated compound. It should make the value for KSP go down. I'm sorry, it should make the value for the solubility go down. And it does, right? It went from 10 to the minus 5 to 10 to the minus 3. So roughly 10 to the 3 times less soluble, or 1,000 times less soluble. So the other thing that can affect solubility is the pH. And the solubility of a substance can be pH dependent, depending on what that substance actually is. Here we have an example of magnesium hydroxide with a KSP of 1.2 times 10 to the negative 11. Now, if we write out the equilibrium expression, we have the Mg plus 2OH So when we solve for the molar solubility, right, again, incorporating the stoichiometric coefficient as the superscript, we end up with S being equal to 1.4 times 10 to the -4, right? So at equilibrium, the concentration of the hydroxide is 2 times the S that we just determined, which was 1.4 times 10 to the -4. So we can determine the pOH, and then by extension, the pH of the solution, which is 10.45. So based on or using equilibrium principles, right, if we do the following, if we were to add hydroxide, right, so if we were to, so if we add OH to this, to the system at equilibrium, we add something to the right side, that will actually force the equilibrium to the left. And what it does, so it forces equilibrium to the left, and as a result, it will reduce the solubility of the magnesium hydroxide. So what do we do when we add hydroxide? We increase the pH, right? So we make it more basic. But to make the solution more basic, we actually reduce the solubility or decrease the solubility of the, in this case, the magnesium hydroxide, right? And again, another example of the common ion effect. So in a solution that has a pH of less than 10.45, what happens to the solubility of the magnesium hydroxide? Well, originally here we have a pH of 10.45. What would make the pH decrease? Well, that would mean adding more protons to it, right? Adding more hydronium ions to it will make it more acidic to decrease the pH. If you were to add more H plus ions to make it more acidic, right? Well, which part of our equilibrium system will respond or will try to neutralize that acid, that H plus? Well, it's the hydroxide, right? So if we added H plus, that added H plus will react with the OH minus, the hydroxide ion. So in other words, we're taking away, it will ultimately lead to the removal of OH minus as it reacts with the H plus. As we take away something from one side of an equation or an equilibrium system, guess what? The equilibrium system responds to replace the amount of stuff that we took away. This is an application of Le Chatelier's principle. So by decreasing the pH, we actually make the salt, the magnesium hydroxide, more soluble. Right? So that's if we were to decrease the pH. If we added more H plus, the OH comes out of the solution to react with the H plus, forces the equilibrium to the right. The equilibrium goes to the right. It makes it more soluble. So a lot of these situations really can be explained by Le Chatelier's principle because they are equilibrium systems, and we can apply that to these as well. Okay, so the third thing that can affect solubility is something called a complex ion formation. And first of all, we need to know what is a complex ion. So a complex ion is just simply an ion containing a central metal cation. So let's say X with a positive charge, positive 1, 2, 3, 4, 5, whatever, that is bonded to one or more molecules or ions, right? So you have your central thing, and then we have molecules or ions that are connected to it. Transition metals tend to have a particular tendency to form complex ions. So we're going to say typically transition metals are involved, right? They being metals will form positively charged cations, and they can bond to one or more molecules or ions. So for example, a solution of copper chloride is pink. So the CoCl2 solution, so this is cobalt, not copper, this is cobalt. 2 chloride is pink because of the presence of these ions here. So this actually has cobalt that is complex to 6 water molecules. There's your cobalt in the middle. There's your CO. And then we have 1, 2, 3, 4, 5, 6 in an octahedral arrangement, 6 of these water molecules. And because of that complex, that solution ends up being pink because of the presence of those ions. Now, if we were to add HCl to that solution, what we'd actually see is that it turns blue. And why does it turn blue? Well, it turns blue because we have a different complex ion that's being formed. We have the cobalt with 4 chlorines attached to it. So there's your cobalt again, and there's our 4 Cl minuses that are attached to it. So the different complex ions have different colors associated with them. There are other examples. We've used copper sulfate, for example, a lot in this class, in lab, for example, and you know the copper sulfate has a very characteristic blue color. That's because the copper ions are hydrated with water molecules, right? So they're very, very common things, and they also affect the pH of different solutions. So when we look at the formation of the complex ion, what they do is they actually increase the solubility of the original ionic compound. We'll take a look at an example here to illustrate that, right? So for instance, if you can imagine an example that we mentioned previously. Okay, so the copper sulfate, for instance, dissolves in water to produce a blue solution. And then the hydrated copper ions are responsible for that color. If you add a few drops of concentrated ammonia solution to a copper sulfate solution, it causes the formation of a light blue precipitate, right? So copper sulfate, okay, is blue. It's a blue solution due to the hydrated copper ions. Okay, if you add concentrated ammonia to it, okay, it forms a light blue precipitate. So blue PPT is actually formed. Now, that happens because the hydroxide ions, OH minus, combine with the copper ion to form copper 2 hydroxide. Well, where is the hydroxide ion actually coming from? Well, the hydroxide ion come from the ammonia. And the more NH3 is added, the blue precipitate redissolves to produce a dark blue solution, this time due to the formation of the complex ion with the copper and ammonia attached to it, right? So if more NH3 is added, right, then we have this formation. This is a very dark blue dark blue solution. And you notice the precipitate dissolves, right? So this then would dissolve the more ammonia we add to the solution. So what actually happens here is the formation of the complex ion, right? This is a complex ion we'll highlight in yellow. What that does, so the complex ion increases the solubility of the copper hydroxide, the copper 2 hydroxide. Right, a measure of the tendency for a metal ion to produce or to form a particular complex ion is given by what's known as the formation constant, which is just another example of an equilibrium constant, but now the F here means formation, and that would be in our example up here, right? It'll be the formation of the copper with the ammonia complex to it can be represented by this equation. So it'll be the products, or the product in this case, divided by the concentration of the reactant. So again, same way we write our expression, same way we write this one. We now use the Kf to represent that process. And in this case, that's equal to 5 times 10 to the negative, I'm sorry, 5 times 10 to the 13. So you'll notice this is a very big, very large Kf value, right? And that means this equilibrium lies to the right. And what that means is in solution, we'll have a very, very small concentration of the stuff on the left, which would be the copper ion at equilibrium. So let's take a look at one more example of how this complex ion formation can affect the solubility. So we've seen this equation before. We have AgCl solid to form Ag plus AQ and Cl minus AQ. What we can also do here is, because on our table, we have an equation that shows the formation of the complex ion that has silver in it and the ammonia. And we can write the equilibrium expression for that as well. So we have Ag plus AQ plus 2NH3 to form, that's AQ, to form Ag NH3 twice. And then we have a positive charge, and that's AQ as well, right? So we know what the KSP for the first one is. We've used that quite frequently. That's 1.6 times 10 to the negative 10. Now the Kf for the formation of the complex ion with silver and ammonia is 1.5 times 10 to the 7. And what we can do is we can add these two reactions together, right? These two equilibrium expressions, we can add them together, and we can apply the same principles we used before for adding together equilibrium expressions as follows. The Ag is going to cancel because they're on both sides of the equation. And what we're left with here now is the AgCl solid plus the 2NH3AQ reacting to produce the Ag complex ion with ammonia. And then I also get the chloride, Cl minus. So when we add these two together, okay, what do we do to our KSP values? When we add them, the KSPs, we multiply them, right? So the K for this combined reaction would be 1.6 times 10 to the minus 10 times 1.5 times 10 to the 7. We evaluate that and we end up with 2.4 times 10 to the minus 3. So if I compare the K value of this to the KSP, what I find is that this is significantly larger than the KSB value. Okay, and what that means then, right? So, 10 to the 7 times larger, essentially. So that much more AgCl, so much more of the silver chloride, can dissolve in the presence of the aqueous ammonia than in H2O, than in pure water. So generally, what we're going to see is that the effect of a complex ion formation is to do what? Well, we've just seen what it does is to increase the solubility of a substance. Okay, and we've quantified that relationship here by looking at two equilibrium systems. We've added them together like we've done equilibrium systems before. We multiply the K values and we can compare them to see the effect that coupling one equation to another one has on the solubility. Okay, so the formation then of that complex ion consumes the metal ion that's produced by the dissociation of the salt, right? So the Ag plus that's produced here when the salt dissociates is actually used up in the formation of this complex ion. As a result, it drives this initial equilibrium to the right. And by doing that, it increases the solubility simply due to Le Chatelier's principle, but we've quantified that relationship by putting some numbers behind it.